Okay, kind of a pretty little introduction. We're going to go now to subtle substitutions. Use substitutions that are a little bit more challenging than the last two I did. Okay, so we have example 3, we have an exponential function. Now, so what you have to know from this thing basically is this. You got to know the fundamental thing is the integral of e to the u du is equal to e to the u plus c. So somehow we got to transfer this integral using that idea. All right. Now there's different approaches on this that you could do. One thought would be maybe you could let u be the whole denominator. You might try that. Okay. Or you might try to simplify. I think when I was working on this integral, I'm thinking that maybe I ought to try to simplify before I even do a u substitution, because you'll probably run into some problems if you just experiment directly with u substitution. So what I'm going to do first of all is I'm going to go through and just simplify this thing. I'm going to write this as e to the x over e to the x minus 2 over e to the x. So I'm going to change that negative exponent to positive. And what I have is a complex fraction, so I would like to get rid of that. So I'm going to multiply the numerator and the denominator by that and just kind of see what happens with this then. Okay, all right, so if we do this, e to the x times e to the x would be e to the 2x. You add the exponents when you're multiplying. E to the x times e to the x is e to the 2x. And when you do this, the e to the x's are going to cross out, leaving you minus 2. So what I'm going to do is I'm going to work with that, and I'm going to see if that will get me anywhere. So I'm going to write this as integral of e to the 2x over e to the 2x minus 2 dx, and I'm going to work with that a little bit. Okay, now I'm going to erase this over here, and then we're going to work with u substitution on that. So sometimes try a little algebraic simplification at the beginning. Okay, now my thought is going to be I'm going to let u be the entire denominator. My thought process on this is the derivative of e to the 2x is itself times 2. So you're going to be pretty close on that by doing that. Okay, so what I'm going to choose to do is this thing right here. That's going to be the u. Okay, now what I'm hoping is when I do the derivative that I'm close to what's left over. So that's what's left over. Okay, so now I'm going to do du. Okay, the derivative of an exponential is itself times the derivative of the exponent, which is 2. And of course, the derivative of 2 is 0. Okay, so you end up having du is equal to 2 e to the 2x dx. So that's pretty close to this. It's off by 2. So what I'm going to do is divide by 2. Really, you're multiplying both sides by a half. So you end up getting du is equal to e to the 2x dx. Okay, and then you got 1/2 there like that. So this thing right here, e to the 2x is going to get replaced with this. Okay, so I'm going to put that in, and we're going to replace that with 1/2 du. Okay, so now I'm ready to go through, set up my u integral, and I'm ready to integrate. Okay, so after we've done that work, we're going to transform this into the integral. Again, e to the 2x dx is 1/2 du. Okay, e to the 2x minus 2 is going to be u, so that's what we're going to do. Okay, that's a real simple integral. So I'm going to pull out the 1/2. So I've got 1/2 integral, and I'm going to write this as 1 over u du. And we know that the integral of 1 over u du is the natural logarithm of u plus c. Okay, so this is going to give 1/2 natural logarithm of u plus c. Then we plug back in. So remember, e is this. So that plugs in there to get the final answer. So the final answer of this problem is going to be 1/2 ln of absolute value of e to the 2x minus 2 plus c. Okay, now this one's actually pretty easy to check. So if we wanted to do a check on this, let's just kind of look at how we'd differentiate that. We'd write the constant. The derivative of a logarithm by chain rule would be 1 over the function times the derivative of that function. Now the derivative of the bottom is going to be e to the 2x times 2. Okay, you're going to notice that those 2's are going to cross out, so you're going to be left with e to the 2x over e to the 2x minus 2, like that. Now that takes you back there, okay, and that's algebraically equivalent to the original integral like that, so that checks out. Okay, so that one you had to simplify a little bit. So go to the next one. We've got some trig, and you're probably going to have to think about identities. A couple of things that come to mind with me is I know that if the cosine x over the sine x is the cotangent x, so that might come in handy. We'll find out. Okay, so kind of keeping in mind this identity, I'm going to work with this a little bit to start with. So let's just kind of work with the algebra. I'm going to write this as cosine fourth to the x, and I'm going to split up the sine and write that as sine to the fourth x times 1 over sine squared x. Okay, now that thing is going to be the cotangent. So this is going to be equal to cotangent fourth x. Then I'm going to write this as a cosecant squared x. Now here's what I'm looking at. One thing that I know is I know if I take the derivative of the cotangent of x, remember that is equal to negative cosecant squared x. So that's kind of going to be the thought that I'm going to use on this. So I'm going to break this integral up into this. So I'm going to rewrite the integral in the form cotangent fourth x cosecant squared x dx, and then we can do some u substitution on that then. Okay, so what I'm going to do is I'm going to let u be this, okay, just not the cotangent fourth, but just the cotangent. Okay, so I'm going to let u be the cotangent of x. My thought process is when I take the derivative of the cotangent, I get negative cosecant squared x dx, and notice that is almost the same as the rest of the integral. So what I'm going to do is I'm just going to divide by a negative, so I'm going to get, or multiply both sides by a negative. You can do that. So you would get negative du equals cosecant squared x dx. Okay? So what I'm going to end up having is u is going to be the cotangent, and then negative du is going to be that part right there. So I'm going to end up having the integral of u to the fourth. Okay, remember, I'm letting the u be the cotangent, not the cotangent of fourth, but the cotangent. And this part's going to be negative du. Okay, so I can bring the negative in front. That's a constant. So I have the integral of u to the fourth du. Okay, we know that that is the integral of u to the fourth by power rule is u to the fifth over 5 plus c, and then we just plug back in. So u is this, so plug the u back in, so you would have your final answer of the problem would be negative 1/5 cotangent fifth x plus c. Okay, so that would be the solution to that problem. Okay, now we can do a quick check. I'm going to go ahead and do a quick check, just kind of remind you how to do this. As you're learning how to do these integrals, you want to learn how to check your answer on these because that practices your differentiation skill. So if I was to do the derivative of my answer, okay, I would write down the constant. We have a chain rule now because we're really doing cotangent x to the fifth. Okay, when we do the derivative of that, we bring the 5 down, leave the cotangent alone to the fourth power, then do the derivative of what's inside. The derivative of the cotangent is negative cosecant squared x. Okay, so that's going to cross out. That's going to leave negative cotangent fourth x. And then we have that negative times negative actually is going to make that positive cosecant squared x. Now that goes back to here. So that's matching the simplified form of that integral, but algebraically that's the same as the original integral. So we have a correct answer. Okay, so that'll give a couple of examples for you of a little bit more challenging u substitution, where you do have to do some simplification first.